All right, I'd like to welcome you all back from lunch, and we will continue this afternoon with the Celsius-Linnaeus seminars, which will be 4 talks. And first, I'd like to welcome Arno Solin from Aalto University in Finland. So Arno is an assistant professor in machine learning, and he's previously been a visiting research fellow at the Department of Engineering, University of Cambridge. He's also been a visitor here at Uppsala and also been active out in industry, working as a senior algorithm developer and team leader at a company called Indoor Atlas. So with that, I'll leave the word over to you, Arno. Welcome. Good to have you here.
Thank you. Can you hear me okay? Yeah. I'm just going to share my screen. With that, I hope you can see the slides I have. It's a pleasure being here with you. I'm like very honored to sort of be part of this sort of like extraordinary day with all of good speakers. Some of them I know from before, and I'm very happy to be here presenting with you. The title of my talk today is a bit unusual in a way. It's an unholy alliance, and the alliance is between probabilistic priors and then like deep learning models. So the like broader message I try to sort of like bring forward here is that like probabilistic priors, probabilistic modeling can play a major role as a building block among like other machine learning tools, which are typically maybe not viewed from a probabilistic viewpoint. And why is that? Well, you typically might need like uncertainty quantification and things like that, but then also then actually bringing over ways of encoding that you know something and that you also don't know something can actually help improve the usefulness of your model or give you better results at the end. And let's see, this work here that I'm presenting is actually joint work with 2 of my students and me, Yushin and Ari. And Ari just defended his doctoral thesis a couple of weeks ago, and Yushin is also defending soon. But this has been sort of a recurrent thing that we have been looking into with them. And I'm actually sort of like using bits and pieces from 2 different paper projects here in the talk. So both Yushin and Ari are actually sort of, they are concentrating on computer vision models, while my own background is in more like probabilistic modeling, maybe a bit more in the theory side. But then sort of, I think this is a nice project where sort of like actually sort of me having some knowledge that they don't have, and they actually having a lot of knowledge that I don't have, and then us putting that together has been a nice sort of like journey for all 3 of us. The outline is that I'm trying to motivate a bit why I'm actually trying to do something like this. I have a nice example of that. Then I'm telling you about depth estimation, how to do like single camera depth estimation. That's like part of like kind of a fundamental problem in machine perception, how to make the machines perceive the surroundings and understand depth. Maybe a bit similar to as humans or animals do. And then I introduced some like probabilistic modeling in the time domain for that problem. And I then try to broaden the scope to more general computer vision problems, where sort of like we are like trying to build like view-aware models with these sort of temporal priors. And that like in probabilistic modeling, that then like links to so-called Gaussian process models, which are nice sort of building blocks for encoding prior knowledge in like classification regression tasks in machine learning. And then I have some further application examples and a short recap. Yeah. The motivation, actually, this is something I've been thinking of like every now and then. And here, think of a rooster. The rooster has its eyes on opposite sides of its head. And we humans, we have like stereoscopic vision. We have so to say like 2 cameras, 2 eyes, And then those are slightly apart so that we get two slightly different images into our brain, and we can infer depth from those two images. But for birds, like the rooster here, that is kind of not the case. I must say that I'm no expert on animals or brains, but sort of, you know that when the rooster walks, it like walks a bit like this. It's wobbling its head. So, and one hypothesis for why it does that is that it kind of tries to like get slightly different images for its two eyes, and then there's some sort of sensor fusion in its head then to infer like the 3D surroundings, the depth of the scenery around it. And in computer vision, this sort of is known as like multi-view stereo. So like you try to get sort of like slightly different views like apart. They only have one camera, but you sort of move the camera like back and forth or like pan it or so to get slightly different angles, and then you try to infer the depth from those images. And this is of course also like related to like acquiring temporal structure from scenery, because the scenery might change. So then, how do you then usually use these multi-view stereo methods? Typically, you have a pair of frames or a sequence of frames of like that one camera you have, and then you have some sort of like nowadays you have like a deep learning model that you have trained with a lot of like data. It's learn like visual cues and how sort of like images relate to each other, and that's the way how you construct that sort of like your depth or disparity map. But this is quite sort of like error prone, and sort of like if the two frames aren't that much apart, if they're too much apart, then it might be very hard for the neural network model to infer the depth. There's a lot of like noise and artifacts introduced. I'll have an example of this later on. So, and of course, like if you have a temporal sequence, you say you have a smartphone that you use, then actually you acquire like pairs of frames over time. And then you would like to have like the associated depth for those frames. So then what you would traditionally do is you would have like a rolling window of frames, and you try to then like use pairs of them to infer the depth map on each point. So this would be like independent pair of frames that you then feed through a trained model. The idea here now for our work is to introduce similar like a priori knowledge that the rooster would have. The rooster knows that it's wobbling its head, but somehow the sort of the frames that it sees should be somehow like related over time as well. So what we do is that we introduce a probabilistic prior that says that, well, if these cameras, the frames at which like the cameras are seeing the world, if they aren't that much apart, if they are seeing kind of the same thing, the field of view is the same, then probably the depth should also be similar. And then again, if the sort of the rooster or the smartphone then turns 90 degrees, then like the scenery is completely new. There is not much relationship between what you saw like one frame ago and what you see now. So then they should probably be less related. So what we want to do is to introduce such a like prior that could sort of encode this sort of knowledge into the latent space of this model. Saying basically that, well, if you're just moving a bit, then the depth should be more related, and if you're like turning completely around, they should be very, very little related to each other. So I would like see this sort of like this thing here as that they sort of these latent states would be kind of coupled with rubber bands. So we would have some prior knowledge of that, but then of course the observations would then be fused with that prior knowledge in a probabilistic sense. And that knowledge, of course, then because if we know how we move our head or how we move the the camera, then we have some knowledge also about the movement of the camera, and we want to include that kind of pose similarity in this prior here. Okay, this might get more like clear when I have an example. So like previous methods, like typically are trained on big data sets, and they often then, in order to get better results, they just use more frames. But then of course you need to wait for those frames to accumulate. And then also the computational load gets like quite high if you have a lot of frames. So instead, like what we want to do is that we kind of use less data, but then couple things over time. So then the question is that, well, all this sounds quite sensible. So that we want to couple things based on how much like the views, the cameras see the same thing, and so on. But then the question is that how to actually like encode this into the model, how to put this into an equation form that we can actually then implement and use. And that is the question here basically now. And what we did in this work was to introduce a like pose kernel that takes in the camera pose, which means that it's the camera location in 3D, and the view angle also like with 3 degrees of freedom. So like a 6-dimensional sort of like quantity, which is the pose. It includes sort of the full characterization of the rigid pose of the camera. And then we introduced a way how to make kernels or covariance functions which tell about the relationship between different views. So basically a way of encoding that similarity metric that between different views. And additionally, in order then to actually make things run in real time, we took one step further and then also constructed like a Markovian model of this kind, where sort of the past is forgotten, and instead sort of like the kind of the local knowledge of how similar the views are is like accounted for. And here's an example of such a pose kernel. So this is actually the local library here at the university. So these are camera poses with the camera frustrums, basically the sort of the opening angle of the camera. And here you can see that the camera poses 1 to 3, the image is taken at like 1, 2, and 3. They are very similar. They're looking in the same direction. So there's like a high correlation there. And then if we compare then like these 1 to 3 and view number 6, which is here, there is not much correlation at all going on there. And then again, if we go back and look at this like view number 9 here, if you look here, there's like again a high correlation to these first views. So like this introduces like correlation structure between what the camera sees. And then again, even though these are like spatially close by, but they sort of look in a different direction, there's again like a lower correlation between like these first 3 and then these last views here. So this is a way of encoding such knowledge into the model. And then like modeling wise, we have like a kind of a neural network that does like access a feature extractor kind of from the image space to like a latent space. And then we have a Gaussian process prior than here over these latent space quantities that are bound together with these like camera similarity view kernel, the view kernel. And like you could view this as a so-called like multi-output Gaussian process model. And we trained the model, then we have some there's like good data in the computer vision field for like training these kind of models. Some are simulated data sets, simulated objects and observations of those, and some are like real world data sets from like different like real world like settings, outdoors and indoors, driving with a car and so on. So there's like quite a versatile set of data, and you can train these models then using that data. So this kind of a fusion between a very sort of like learning-based neural network model and then quite strong prior knowledge in the time domain that things that see the same thing should behave the same. We have some results on some like benchmark problems compared to other models, and it turns out actually that this is a very beneficial way of doing this. We get state-of-the-art results in these benchmark tasks. But more interestingly, so I like practical applications and practical demonstrations, and then we had this idea that, well, if this should be then so efficient and such a good approach for this, then it should work also in real life. And then my idea was that, well, why not port all the codes and models we have into C++ and Objective-C and actually run this thing on an iPad. And this was sort of like easily said. And then actually Yushin spent quite a deal of time on like implementing this, but I think it actually turned out to pay off. So this is actually this office where I'm sitting now. This desk is actually in the same laptop and the same chair here, as you can see. And you're going to see a video of screen capture from my iPad. And what you see here is that there's the previous frame and the current frame. So this iPad only has one camera. And then this is the depth estimate for the current frame. And what it really does is that first, it hasn't like, when we start this thing, it hasn't really seen any data previously over time. So then you see kind of the noise result that you would just get from the neural network. But then when it keeps going, then the GP, the probabilistic prior kicks in, and you can actually see how much it improves the results. Let's see when it runs. Starting up the app, there you can see the frames. And now you saw that after a couple of frames, the GP prior kicks in, and you actually get quite good depth estimates just from these like single camera views of the scene. And probably this could be improved a lot and made more real time. Now it's like 2 frames per second, but we were quite happy with that already, because typically like these models in computer vision, they need hefty GPUs, and like actually like any of the other previous models, you need a huge computer to run these things. And even though you only get like, it takes several seconds to evaluate one thing. So now if you can, like on an iPad, computing everything locally on an iPad, get 2 frames a second, just with our hacky codes, we can be very happy. Then let's try to generalize this a bit, like beyond just depth estimation. So of course, like in any computer vision tasks, you might be interested in actually sort of encoding knowledge between camera views. And of course, also, you might want to be interested in actually sort of quantifying some uncertainties that you have in your model related to the inputs, or then do so-called like interframe reasoning. You have one frame observed right now, and then one frame observed in 5 seconds. But then the question is that what happens in between? The world doesn't stop. So something happens in between, and then you might want to predict something there. You might want to know what the uncertainties that you have in between the frames and so on. So that's kind of what we are interested in here. So of course, like if you think of the camera pose, there's like the camera like view angle, the orientation, and then the translation. So the translation part is fairly simple, but then like the priors, like over the orientations, was sort of the main question for us, because there's been a lot of like methods for that, but nothing really sort of like of the kind that we want to have. So we dug a bit further in this space, and I have some examples later on. And I'm saying that there's a lot of like methods for this, and like in the like a Gaussian process community, like typically how you build these models that you have, like you look up pre-existing covariance functions, like building blocks of your model that you can encode different properties with, be that then periodicity or continuity of the latent sample functions or some other properties that you want to have. And then you combine these things. And what you actually see that people have used before is that because orientation angles are angles. They are like, it's a 3D, you can like form the Euler angles for that. So you have three angles, and the thing that you might then end up using would be that just taking like a product of so-called like periodic covariance functions. But that's a horribly bad idea. That's sort of like a danger zone and like a common pitfall that we stumbled upon people had done previously. Because you get all these problems with gimbal lock and ambiguity with the orientation angles. And that can be easily shown that it's not a good approach. So instead, then we explored some other options, but then what we end up using is to actually try to generalize the like vanilla, well-known sort of theory of like 1D periodic things to higher dimensional periodic things, where the inputs would not be just single angles, but actually rotation matrices given either in terms of matrices or angles or quaternions or whatever like measures of orientation. And there's nice derivation to this, but the end like kernel or covariance function that we end up with is actually surprisingly simple. And this can be seen as the like direct generalization of the 1D one-dimensional periodic covariance functions, which been around for quite a while. And then we actually sort of like, well, we got the model, then we want to try it out in actual sort of tasks in computer vision, like different. One task was to just include it in pre-existing models. There's this model that is sort of like can be trained on objects or faces or whatever, and then we used it for like predicting then new view angles of like unseen, for example, in this case, chairs. And this worked like pretty okay. The model has its own like it's a like variational autoencoder model. It has its own problems in training and so. So we also looked beyond that. We looked into doing inference in the latent space of so-called generalized adversarial networks. And you might have stumbled upon these GANs recently, because this being quite celebrated models in generating fake things, be that then generating faces of people who do not exist, generating fake food or fake bedrooms or fake cars or whatever. So they are kind of the state-of-the-art models for generating things. And they are actually quite impressive. You can get very impressive results for example, generating like people's faces that do not exist. So we tried working with these GAN models. And in GANs, they are really meant for generating things. So actually sort of like reconstructing things is not their strength. And we had to use some like special made tools for that then. So for example, here we have two volunteers who have volunteered for this study. And then you can see the reconstructions using the GAN model of their faces. So you see that, for example, in this case, the reconstruction of the glasses was clearly quite challenging, but like overall, I would say there are some similarities in the faces. And now, what we actually want to do is, this is an example of an independent Gun reconstruction. So we have observations, we have like a video observation of the camera sort of like looking at these people. And we could, of course, then do like noise reduction or things, but let's try something quite extreme. So I have two inputs here in both ends here, and I want to interpolate what the person looks like then when the camera sort of moves from this pose to the other pose. And those camera poses in between are known. So those we can give as inputs to the prediction we want to do with our, we have the as a prior for the like relationship between this view and the other view. We have our like view kernel now, which generalizes the rotation and it's multiplied by a translation rated kernel. So here you can see, this is a video. So here you can see the ground truth and then the predicted result. So these are all filled in by the model then. It struggles in the end because the model can't really reconstruct when the head is like in a very different angle, but then it follows the movement of the camera actually quite well. And the nice thing is also that we kind of out of the box, we also get some uncertainty estimates of how uncertain we are. So the darker the colors, the more uncertain it is about things. So here in the end, you saw that it's very uncertain about the kind of the angle of the face. So then it's uncertain towards the middle because there's no observations there. And then it's very certain about the endpoint, as you see, because it kind of knows that observation. So I presented you kind of a combination of two things, kind of like a deep learning based, like very like heavily learning based machine learning models, which can then be fused with like strong prior knowledge from kind of sensible things. Like here, the prior knowledge just came from the fact that, well, the end outcome should be more similar if the camera hasn't really moved, and less similar if the camera moves. That's kind of what we encode with this prior knowledge. And then, of course, the actual sort of where the magic happens is how to do an inference, how to do predictions, how to do the learning in these joint models. And I think there's a lot of like work to do in that space. But at least these things that we tried out played out very nicely. And I'm very enthusiastic about this project. It's been a very fun project, and things actually worked out. It's sort of like you have an idea sometimes, and then you try it and it doesn't work. So this was kind of the opposite here in this. And that's why I kind of call it an unholy alliance, because people aren't typically combining these things in these ways. So these are kind of separate ends of the like machine learning community. But I think there is a lot to sort of win by sort of like looking into both probabilistic models and then these sort of models that have typically been viewed as sort of like not probabilistic at all. And then I'm still very happy that we went through the trouble of actually porting things to run on the iPad, because that's really showed that you can actually do these things in real time, even though they are like sound fancy and they are big models. You can really do that in real time on just standard hardware, such as my old iPad. Yeah, the examples here that I went through are from these two papers, both like published in well-known machine learning and computer vision conferences. And actually this later paper was presented just last Friday. So it's really like fresh in that sense. Great. I think my time starts to be up. I'm happy to take any questions if you have at this point. And thank you.
Thanks a lot, Arno. So in the interest of time, I think if there is any quick question, we can take them now. Otherwise, we can also return to this during the discussion after the talks. And for the questions, maybe I should have said that in the beginning, but just type them in the Q&A function and we will be able to address them. But I think in the interest of time, I think I will actually save my questions until a little bit later and then leave over to Mate so we can keep up with the schedule. Thanks a lot, Arno. Thanks a lot.
Thank you, Thomas. And it is my pleasure to introduce the next speaker of the symposium, who is Xiaodong Zhou. She is a professor and the deputy head of the Department of Materials and Environmental Chemistry, and also the chair of Inorganic and Structural Chemistry at Stockholm's University. And she originally studied actually physics in Peking and Beijing, and moved to Sweden for a PhD in structural chemistry. She did her PhD in '95 in Stockholm, then moved to Lund for a postdoc, and returned to Stockholm later on. She started the Berzelii Center, excellent on porous materials, and she's renowned for developing new electron crystallography methods, and also softwares for accurate atomic structure determination. And she has solved a large number of complex structures of zeolites and mesoporous catalysts or crystals by transmission electron microscopy, and also an expert on inorganic open framework materials, metal organic frameworks, and porous materials. And today she will talk about 3D electron microscopy for us. And with this, I would like to give the work to you, Xiaodong, and look forward to your talk.
Okay, thank you very much. Today, I'm going to talk about a new technique. It's 3D electron microscopy as an important tool for developing new porous materials for sustainable society. And so I'm from Stockholm University, and we are working in materials environmental chemistry. And the 3D atomic structures are very important, and they determine the properties and functions of all materials, all molecules. You can start with like diamond and graphite that builds with just a single carbon atom, and they have very different properties because of the structure. And of course, the pharmaceuticals, and today, like the coronaviruses. And all this, we need to understand their structure, and in order to find their properties and find their functions, and also find the medicine and the antibodies to kill the disease and the viruses. And for my research, I'm working on nanoforest materials. And why they are interesting? Because they have very large surface area and also pore volumes. And for example, you see this, everybody knows, and you can see that you can absorb a lot of water, take a lot of water, and anything. And for us, we are working with nanopores, so it was very, very small pores that you see here, and they are ordered. This is a picture of zeolite, and you see the white features, they are ordered pores. And these pores are in the size of the molecular dimensions. So it's very selective to act as a molecular sieves that you can absorb certain molecules and refuse to other molecules to coming into the pore. Very high selectivity. And actually they have very rigid structures. And for example, it's built by different building blocks, and they are very important for heterogeneous catalysis and gas uptake, molecular uptake, and the separation. And it has very large structural diversity. And I just show you here, there are two types of porous materials I'm going to describe here. And one is zeolite. And zeolite has been used everywhere. And for example, all the petrochemical industry, they are using zeolites to crack all the raw oils. And actually, zeolites are very simple. It's mainly built by silicon dioxide, and with some aluminum or other elements incorporated. And this is the building unit, like just the silicon and connected with oxygen. It's like a tetrahedral, and they are sharing and build all the frameworks. And so if you look at one of these building units, and each of this corner, that is silicon tetrahedral, as you see here. And this can act as a building units to build many different types of materials, even the main composition is just the silicon dioxide. And as you see here, so depending on how they are packed or this building unit, and you can build very many different structures. And actually, by predicting all these structures, there are like millions of portable structures that can be built using just a very simple building unit. And another types of materials, that is metal organic frameworks, and they are built by metal clusters, as you should see here, and also organic molecules as a linker to connect all these metal clusters. And actually, you can see that they are very, very diverse and can be tunable because you can choose different building blocks and build different structures. This yellow box shows the empty area of this structure. And you see that you can easily change the linkers and also change the metal clusters and build many, many different types of structures. And so you can really design porous materials that has certain functions and also certain properties, and by tuning the channels and the pore size. And these materials are very interesting because really they have very large surface areas. 1 gram of this material, for example, metal organic framework, has more than 5,000 square meters per gram area. And this is like 1 gram of the material can have the surface area cover the whole football plant. And so these are the interest why porous materials are interesting. As I said, you need to know the structure and how to get the structure. Actually, most of the structure were solved using single crystal X-ray diffraction. That was already demonstrated by Brock and Brock more than almost 100 years ago. And what we do is that you have a crystal and you have an X-ray beam passing through the crystal. It will diffract. You get diffraction patterns like spots. And then you rotate the crystal and you collect the data in different directions, get the 3D data. So this is the data you will show to combine all of this data. And after that, through this data, you see everything. You can see a lot of spots, and they are periodically distributed. That is because of the nature of the crystal. And from this, and we can determine the unit cell parameters, which means it's how the repeating unit is built of. And also based on the intensities you see here, you will be able to extract this intensity, and using this intensity to get the atomic structure of the model. And so this has been used for most crystal structures. And the problem is that you need to have very large crystals. And actually, if you use synchrotron as an X-ray source, you can reduce the size of the crystal down to a few micrometers. But for the smaller ones, the nano materials, it is difficult to study the structure. And actually, this is how electron crystallography comes. And you are using electron microscopes. And just a comparison you see here. And here is the crystal structure, crystals you need. And we can reduce the size by more than 100 times. And this kind of crystals can be studied by electron crystallography, electron microscopy. And this is almost invisible crystals, and you don't see it by just through the microscopes. So this looks like a powder. And for a lot of structures have been solved by X-ray diffraction. Like now they have more than 1 million crystal structures in the Cambridge Structure Database. This is a database mainly for structures contain small molecules and contains organic molecules. And there are also a lot of structures for the proteins and or the biomolecules. And very few of them were studied using electron diffraction. The reason was that it was skeptical about electron diffraction. And the early days, even in the textbook, it was written that electrons are scattered strongly by their interaction with the charges of electrons and the nuclei, and so cannot be used for studying interiors of solid samples. And actually, that is true, but we can make the use of the strong interactions of electrons with atoms, and to be able to reduce the size of the crystals needed for studying by using electron crystallography. And what electron microscopy can give you, and we can get both images, diffraction, and also chemical compositions. And so it's a very complex instrument. And first, I will show you something about the imaging and the diffraction. So you see here, this is an image taken from electron microscope, and this is corresponding diffraction patterns. What I would like to show that actually it is much easier to take electron diffraction patterns, and also the resolution you obtain is much higher. So this is typically the resolution of this image, but on the same crystal, when you take diffraction patterns, you get a much higher resolution. And by combining all these two images and diffraction pattern, it was possible already to show that to solve the structure using electron diffraction. Sorry. And if you have complicated structures, you need to combine data from different projections. So here you see here, and we can obtain the two images, and with very small area, if the crystals are disordered, like so, it's not very periodic, and with this nano-sized area, and it is possible to obtain three-dimensional structures. So this is a zeolite catalyst. And but it's much easier to take electron diffraction data. And during the last decade, and different groups have been developing 3D electron diffraction, or called micro-ED. Basically, you're using a standard electron microscope, and you tilt the crystal inside the microscope, you collect all different diffraction patterns. And this has been made a big impact in the field, because now we will see it is possible to solve the structure for a very difficult structure using electron diffraction. I give you one example that is a structure of zeolite, and actually it was discovered in the early 1980s, and it's from ExxonMobil, and the crystal was very small, and it was not possible to get the structure. Using the 3D electron diffraction, so we basically can collect the diffraction data and in 3D, and this is the structure we obtained. And this is a very interesting structure, and we found that by looking at the building unit, that is this one, and there was one previous one which was known, and it was possible to build many different types of structure using actually the same building blocks. As you see here, different colors shows the building blocks of the zeolite. And this has a very pore that you show here, and this pore is exactly the right size that can separate carbon dioxide with other gases. That's what you see here. This is the uptake of the carbon dioxide curve, and this is the partial pressure in the x-axis. As you see here, when you have very little carbon dioxide, and the material absorb the carbon dioxide directly, and the other gases are has very low absorption uptake, and that means that this is a molecular sieve that can take CO2 but remove other gases. And using this property, we can capture carbon dioxide, and by like changing the pressure slightly, as you see that, and so this can be recycled many, many times in this way to separate carbon dioxide from the other gases and to be able to capture the carbon dioxide. And another example is a microorganic framework. And so this data was actually collected very just within 70 seconds. Very fast data collected, you took the crystal in the microscope, and the data was very had higher resolution, so 0.8 angstrom. And using this data, we find out that actually this is a very interesting microorganic framework. And as you see here, it was built by titanium zirconium clusters. Titanium has a very important property as a photocatalyst. And with zirconium, it makes the framework much stable, as you see here. And this is a cluster building unit, and it was connected by our organic linker. By functional the organic linkers, it was possible to get a very nice photocatalytic properties of this catalyst. And as you show here, you can tune the band gap using this by changing the functionality of the linkers, and together with the platinum, and you are able to make a very good hydrogen catalyst for hydrogen evolution. And another example, we are using the linkers as a functional group. And this linker is a porphyrin, as you show here, and you can actually put different metals within the porphyrin. And it can use zirconium as the cluster and the porphyrin to build another microorganic frameworks. This is a small crystal, as you show here. We were able to get good electron diffraction data, and from the data, we are able to obtain the 3D structure of this microorganic frameworks. And you see here, it has a pore of molecular dimension, which means that the water molecules can easily go in and all the other molecules. And specifically in this case, we're able to see that actually this is a porphyrin, as you show here, and it has a pore, and also that the distances between the porphyrins can be tuned. And so this has so by tuning the spacing of these porphyrins, and we're able to tune the oxygen reduction reactions activities. As you see here, so you can make many cycles again, and to have the very nice catalytic performance of this book. And a third one example, it is also microorganic frameworks, and it's aluminium microorganic framework, and as you show here, very, very small crystal, 50 nanometers, and we were able to get this beautiful crystal structure. And this was built by a chain of aluminium chains and connected by the linkers, as you see here. It has a surface area of 1,250 square meters per gram. And this tends to have a very nice property for water uptake. If you look at the curve here, this is the partial pressure of the water vapor. And when it comes to about between 0.2 and 0.3, and there is a very rapid absorption of water in the material. And at this time, so it's like has a about 37% of weight percent of the water can be absorbed in the material. And with this one, you see that it has a different temperature. So by changing the temperature, the water absorption will change. And this is a very useful application. One thing is that it can take water harvesting with very dry conditions. At the 0.3 partial pressure, humidity is very, very low. And you can capture water And another thing is that by using the softening and desorption, you can have absorption of water to make a chiller for cooling. And so it's a very, very low temperature cooling, and this will be able to save a lot of energy. And also the material is very stable, and they can recycle more than 5,000 times. So this has a large potential for applications at more. And using electron diffraction, and it was possible to solve a lot of structures, and now we are in the way we're competing with X-ray diffraction, and we can solve a lot of new theorized structures and metal organic frameworks. And this is a general technique. Actually, you can study pharmaceutical compounds, molecules, and also you can study proteins. And we have have applied all this technique to different types of materials. So it's not only on porous materials. And in order to make this technique more easily available and faster, and we are developing different techniques. One is called electron diffraction, and we want to make the data collecting in an automated way and being able to collect a lot of data. And so this was done by my former postdoc staff, as you see here. This is a typically EM grades. And when you look at this grades, you will see that they are, you can collect the data to go through each grid. So this grid holds, and to take a picture, and because we can see the picture, and we can find out where the possible crystals are located and go there to take diffraction pattern. So this was done in an automated way and very fast. 3,500 crystals can be studied within an hour, and this makes it possible to really scan a lot of particles within the sample. And by doing this, and you have a lot of diffraction patterns. Of course, it's difficult to study one by one manually. And when my former postdoc, Jonas Armstrong, has developed this machine learning, and they used the deep convoluted neural network to study, distinguish the diffraction patterns, what types of diffraction patterns there are, and bad and good. And he used like 78,000 diffraction patterns to train the CNN. And after that, what you can say that you give a score, and you see, okay, when you have a very nice diffraction spot, we think that they are good diffraction pattern. Otherwise, they are bad diffraction patterns. And in this way, we will mainly focus on the diffraction patterns we would like to, we're more interested. And using this technique, it was possible to actually make phase size analysis if you have a powder with different types of materials, so you don't know what they are, and you can use this technique. And basically, they can go to each of these particles and find out not only the structure, phase identification, and also the orientation of these particles, because we have a diffraction pattern. And also we can do phase analysis just in a very fast way. Like this is a typical data collection. More than 1,000 particles have been studied within half an hour. And then we will sort out all these diffraction patterns, as you see here. Actually, among of these diffraction patterns, and 494 will have similar diffraction from one compound, like the diffraction pattern looks like this. And there are 6 other crystals that show a very different kind of diffraction patterns. And actually they are coming from impurities. By looking at all of them, of course, you can go to each of these diffraction patterns to find out what they are. And if you don't know the phase, in this case, we can collect again the 3D electron diffraction data. And from this data, we were able to actually to find what they are. And we can also go there to take the chemical compositions, that is the energy dispersive spectroscopy on exactly this particle. And by this, we know that this actually is starting materials carbon oxide. And so the data collection can be automated. And then we would like to make the data processing also in an automated way. And so this is a data collection that typically, as you see here, we can collect 3D data now, go to each sample and find the sample and filter the crystal and in order to get the 3D data. And so this is how we are collecting the data. When the data is collected, actually we will apply the data processing directly online and to be able to find out what crystals this particle corresponding to, and by finding the unit cell parameters. And because each unit cell parameters will be related to certain materials. And after that, when we have all these unit cells, and we can analyze what we have in the sample. And this is the case to see that when you have a mixed phase, in this case zeolite, we can make a clustering of the unit cell parameters to see how they are grouped together. And in this case, you see this is the hierarchical cluster analysis. And we find out actually we have a bigger group of crystals that corresponding to a zeolite called ZSM5. And we have another group of zeolite that is corresponding to zeolite moissanite, and there are also others. By looking at these two group of zeolites, and actually we can do a further analysis by clustering their intensities, not only the unit cells, and we can further divide them into different groups. In terms of the ZSM5, you see that actually the unit cell changes, there are still different types of groups that could be corresponding to, like, you have different modification of the crystals, and the unit cells can be, the intensity can be different. And also this is a moissanite. And in this way, we're able to like group this one, probably merge this data to solve the structure. So these are the structure, zeolite structure you will obtain from this. You see that these are the pores of the zeolite. Actually, this has been can be also applied to many different structures. And as you see, these are the different zeolite structures, and also microorganic frameworks also work can be applied. By doing all this, I want to conclude that the evolution of electron diffraction techniques has been developed very fast during the last years. First, it was studied with a stepwise rotation electron diffraction. So the data has to be collected in about an hour. And then we will use the continuous rotation very fast. And the data collection has been reduced to almost less than 1 minute. And with this data, and we developed the techniques that can directly treat the data and make track the crystal and look for different crystals for crystal searching directly, and the data will be collected in an automated way within less than 1 minute per data set. And also theory electron diffraction can be used and to study the different phases in the sample, and there will be even more, like several thousand particles can be analyzed per hour. And so with this one, all the different techniques now in combination with the automated data processing and structured solution pipeline we're developing, and then we were able to show that now electron diffraction techniques can be used to look at the discovery of new materials, and also to study their atomic structures, and using this to explore their applications and functions. And with this, I would like to end my talk to thank all my students and who have contributed to the work, and they are working in different fields from zeolites, microorganic frameworks to proteins, and so that specifically the people who have been involved in developing the techniques, Wei Wan, Hong Yi here, and the staff, and Bing Wan, and the Hao, Bing Jin, so Bing Jin, and so they are contributed a lot for this work, and I would also to thank the collaborators for the next challenging Sanford for me, and thanks funding agencies. And finally, I would like to thank all of you for your attention. Thank you.
Thank you very much, Xiaodong. It was a really impressive talk. I see that we are a little bit behind the schedule, and therefore I would like to ask everyone to keep the questions for the panel discussion, and I would then give back the word to Thomas. Thank you very much, Xiaodong.
All right, then it's time for me to introduce Niklas Volstrom, who is an assistant professor in machine learning here at Uppsala University. So Niklas received his PhD in 2015 at Linköping University, and then came here as a postdoc and now as an assistant professor. He'll talk to us a bit about the interconnections between physics and machine learning. So please, Niklas.
Yes, thank you, Thomas, for that introduction. So can you hear me? The mic is working. Yes, thanks. Then I will share my screen. I guess you can see that screen as well. So yes, I will talk about machine learning, and especially physics-informed machine learning, how data-driven machine learning models can be used to leverage, and how physics can be used to leverage data-driven machine learning models. And the examples I will show is joint work with quite many of my colleagues from here from Uppsala, in Linköping, in Delft, and Aalto, and also in Australia. Okay, so as Neil pointed out already in his talk this morning, models are quite crucial in quite many different scientific disciplines, both to understand the world around us, but also use that as a tool to gain new knowledge. So models are used and are relating things that we do know with things that we don't know, but want to learn more about. So for example, if you would like to predict the next solar eclipse here in Sweden, and you know the present position of all the celestial bodies that are of relevance for doing this prediction, then you can, with the appropriate model with high accuracy, predict when that next total solar eclipse will occur. And in Sweden, we have to wait quite a bit, more than 100 years, unfortunately, for that to happen. Another example, completely different, more like familiar to us in the setting of machine learning, is a task of image classification, where we know an input, an image, in this case, an image of a church. And we can use a model to predict what that image illustrates, in this case, a church. Okay, so that is two different settings where a model can be applied to transform something that we do know to something that we don't know, but want to know more about. But how do we find these models? So basically, it's like you can boil it down to two different strategies how to find models. So in the first example, with this solar eclipse example, you can quite accurately do this prediction, or very accurately, by using the physical laws that are governing the planetary motions. So here we have quite very little uncertainty involved. So you can do this prediction quite well based on these physical laws. And the other extreme case in the second example, you don't use physical laws to find that model. Instead, you do employ a data-driven approach to find that model relating these two, this input with output. And that is by collecting a whole bunch of training data, which in this case is a whole bunch of images, which you have labeled each of them what that image illustrates. And you learn a model based on that amount of training data. And that model can now be used in a new setting where you feed in a new yet unseen image. And that model can predict what that image illustrates. Okay, and in physics-based machine learning, we sort of want to make use of both of these techniques. That you do want to have a data-driven machine learning model, but you want to leverage the performance of that model by also including the physical laws that are governing the process that on which this data has, what the process that this data is about to explain. And how to do that combination of both having a data-driven model and making that model able to also obey the physical laws is not a trivial task. And it really depends on the problem how to do that in practice. So finding models that can be leveraged by the physical laws and still be data-driven is, I would say, still quite an active research field. How these models should be posed. So you can see that the two extreme cases of finding models: first the first principles, physical laws, and the data-driven. And so the data-driven approach is, I mean, you do, as soon as you employ a model, you do make some sort of assumptions. So you would say that no models are like completely data-driven. You do make some sort of assumptions about the problem you're about to model. For example, if you do know that you have an image classification task, you employ, of course, a model that is tailored for processing images. And also the first principles models, I mean, these physical laws has once been empirically validated based on data, obviously. But then you can employ these physical laws in a later setting. So the three examples that I will show from my own research, which I would argue are lying sort of in between these two extreme cases. With the first two examples deal with the magnetic fields. Where in the first examples do magnetic tracking, where we track a magnetic object based on magnetic readings. Second one, where we make a magnetic map of an indoor environment. And the third example is a strain field reconstruction. And I will come back to that. So just something very short about magnetic fields and the sensors that we use to measure these magnetic fields. And these are magnetometers. And magnetometers are now mounted in every smartphone that is available, almost. And hence, these type of sensors are nowadays mass-produced and therefore quite cheap. And they are quite small sensors, and also they have a very low energy consumption. So since they only passively measure the magnetic field that is surrounding that sensor, which makes them quite attractive for various positioning and mapping applications. And the common use for such magnetometers is to provide orientation information, to use it as a digital compass. so you can know the orientation of your phone relative to the north direction. My use of these sensors have been slightly different though. So I've used in settings where you can, with these magnetometers, can provide both position and orientation information. And the first example again was this magnetic tracking. And the second example is the magnetic mapping of these two. So I will first explain this first example. So the setting here is that we have a sensor network of magnetometers. In this case, we have a sensor network of 4 magnetometers. We have one sensor in each of these corners of this device, measuring the magnetic field in all 3 Cartesian directions, both in X, Y, and Z. And then we have a moving magnetic object that is moving in the vicinity of that network. So what we have, and what we want to know is the position and orientation of that moving magnetic object. What we observe is the magnetic field measured by each of these 4 magnetic sensors. And here we have a physical laws governing what the magnetic fields look like around such a magnet, the magnetic dipole model. And based on that, we can take all these readings and compute both the position and orientation. So in this setting, which is quite much towards the physical law end of the modeling spectra, we don't really have much training data modeling training the models. We have some training data calibrating a few parameters in the model, but except from that, most of the model is based on the physical laws. So here's one example which a few master thesis students did using this positioning technique. So here we have a magnet mounted in this handheld device. With these sensor networks, we can determine its position and orientation in all 3 Cartesian directions. And here they have used that technique to build sort of a 3-dimensional input device to a computer, and use that 3-dimensional input device in a program where you can model a 3D object by pushing and pulling different surfaces of this object. And they also made this in a virtual environment, which you can actually observe this also in 3D. Another sort of application of this first example with magnetic tracking is traffic surveillance, where we don't positioning the small magnets, but rather bigger cars. So we treat them as dipole objects moving around, and then employ various magnetic sensors along the road. And these sensors are equipped with solar cells and have a quite small computational budget. So you have to find quite cheap, computationally cheap processing methods to actually process this data. And with this information, you can count like the number of cars, you can determine its driving direction, and also which type of car it is, the weight of its metallic magnetic weight. Okay, so the second example where I've used magnetometers and magnetic fields is related to this magnetic mapping, where we want to build a map of an indoor environment. So in an indoor environment, the magnetic field is actually not that homogeneous, since you do have metal structures in the floor, in the walls, in the ceilings, that makes the magnetic field looks a bit different depending on where in this indoor environment that you are located. And what we want to do is to find a magnetic map of that indoor environment. since when we have that map, you can use that map in a later stage to localize yourself within that map. Since in an indoor environment, like GPS, are not working as it does outdoors. So hence, in indoor environments, you have to find other techniques to do that type of localization. But in the first step, we need to have that magnetic map. So what we want to know is the magnetic field in every single position in this indoor environment. We collect training data, which is that we collect the magnetic field at just a few positions in this indoor environment. And we want to sort of interpolate this magnetic field. And we want to do it in such a way that it satisfies the laws that we do know that these magnetic fields should obey, in this case, Maxwell's equations. So to do this, we use the machine learning model which Arno already talked about in his talk, namely the Gaussian process. And in that Gaussian process, which is by construction, a quite data-driven model, in the prior of that Gaussian process, we can modify that one such that the magnetic fields that this Gaussian process is describing by construction will satisfy these physical laws. So this is actually also a joint work together with Arno and Manon and also Thomas. Here is, I can show this from the beginning. Here we have a robot which is equipped with actually a few magnetic sensors and also some optical markers so we can determine its position via optical positioning system. And while it's driving around, it's measuring the magnetic field. And here, the magnitude of that magnetic field is now illustrated in this color map. And the transparency here is reflecting the uncertainty of our model. So at places where we don't have any color, where it's very transparent, we are still quite uncertain about the magnetic field. And at places where we do have color, we are more certain. And again, the color itself reflects the magnitude. So here we collect the data and train a model. And that model is also leveraged by the fact that we do induce these physical pre-knowledge that we do have about these magnetic fields. Okay. And then I have the last example of strain field reconstruction. And so this gives some intuition about this. I have this magic square. We have a square of 3 rows and 3 columns. In each of these entries, you have a number. And then you can compute the sum in each diagonal direction and in the row and the column directions. And now we sort of want to invert this problem, that we say we do know these sums around it, but we don't know the entries in this matrix, what numbers should be there. Okay, so that is sort of a intuition. And then the actual problem in this strain field reconstruction is that we do have an object, in this case represented with this, this green object. On that one, we apply some forces in different directions, which in turn will make that there will be a strain in this object. And we want to estimate that strain field. So in each single position, you have a strain represented by a 2x2 matrix, a symmetric matrix, which tells us how much the object has been deformed at that very point. And the way we can estimate this is by shooting neutron beams through that object in various directions. And without explaining the physics behind this too much, so what this neutron beam is measuring is sort of the average strain along that path that this neutron is passing through that object. So it will be sort of an integral measure of the strain along that path. So we shoot neutron beams in various directions and measure that average strain along that beam. And also here we employ a Gaussian process then to model that strain field. In this case, a multidimensional Gaussian process, since this strain tensor has 3 unique elements. 2x2 matrix, which is symmetric, so 3 unique elements. And in addition, we also know that strain fields also should obey some physical laws. In this case, the so-called equilibrium constraints. Which makes sure that all forces are in some sort of equilibrium and have reached some steady state here. That is not continuing to deform, but has ended up in some sort of deformed state where it's a constant. Okay, so we can do the same strategy that we did in this magnetic fields example, that we can adjust our prior in our Gaussian process, such that by construction, before we have even collected any measurements, all functions that this Gaussian process is describing are guaranteed to obey these equilibrium constraints. And some experimental results here that we have done, or not I have done, but our physics colleagues in this work have shooting neutron beams through this C-light type of object. And before that, we have applied forces in different directions. The first row here, they have computed what the strain field looks like with the finite element methods. So in the case we actually do know the material, you do know at which points you have applied the force. But now we want to sort of reconstruct that strain field without knowing the forces, but by only shooting these neutron beams, and then use our Gaussian process model to predict this strain field. And that is what you see in the second row here. So the 3 different columns are the 3 different unique elements in this symmetric 2x2 strain tensors. So we can see quite a big similarity between what our Gaussian process models predicted and what the finite element method were able to actually. So you can see the first row as sort of the ground truth, and we are quite close to that one. And this last row here is also the uncertainty of our Gaussian process model, since that is also one great benefit with that Gaussian process model, that it also comes with uncertainty of how well we actually, how certain we are about our prediction. Okay, so to summarize this, this is physics-based machine learning. We make use of physical laws of first principles to leverage the performance of data-driven machine learning models. And I presented 3 different examples from our research where kind of exemplify this, where we, in various degrees, have combined these 2 modeling approaches. Yeah, so by that, I thank you for inviting me for this talk, and I'm happy to take any questions now or at a later stage.
Thanks a lot, Nicholas. Let's see if there are any questions. I think we might have time for one or 2 questions at this stage, if there is one. Again, use the Q&A function to ask your questions. Can I ask a quick one? What do you think? So you use the Gaussian process in various ways here. what other developments would be needed to this mechanism to do more exciting things in the future?
Yes, so one limiting factor, at least if you just do that plain Gaussian process regression, is that you're limited just with just linear constraints, at least if you want to make sure that after you have completed linear constraints, that your model is still a Gaussian process. So to include, for example, nonlinear constraints, and you do have to make some approximations. You can also, and there is also quite recent advancements in making neural networks also to be more physical informed, and they don't really, I mean, they can handle these nonlinear constraints quite well. So, and then maybe a combination of Gaussian processes and neural networks, which also Arno pointed out. And since the neural network is a limiting factor that you don't, at least in its basic construction, does not provide uncertainty quantifications, whereas Gaussian processes do. So both of them have like pros and cons. So maybe sort of combining the strengths of these two methods could be a promising direction.
Mm. All right, let's thank Nicholas there and move on with the schedule. So I'll hand over to Matti again.
Thanks, and it's my honor to introduce our next speaker, Jan Strife. He studied chemistry in Bonn and then did his PhD at Bonn University and the University of Strasbourg, and moved then to Caltech for a postdoc and started his independent research in Freiburg about 10 years ago. And he is just about to move over to Uppsala University. So we warmly welcome you, Jan. He is an expert on the synthesis of heterocycles, does mechanistic studies of catalytic systems, develops metallocene catalysis, catalytic or expert on catalytic cleavage reactions especially. And he's also an expert on radical reactions. And he will today talk for us about both bond forming and bond cleaving reactions. And with that, I leave the word to you, Jan.
So, hi, everybody. Thanks, Marta, for the introduction. It's a great bit about our research. And I will try not to go too much into detail today and just focus more on the concepts of our research. I want to start with we as organic chemists, we often think about taking small molecule precursors that are commercially available and turn them into more complex molecules like the one that you see down here. It's called Taxol. It's a famous anti-cancer drug that is usually isolated or has the first time been isolated from the bark of some pine tree and is now synthesized semisynthetically. It's a powder and it's quite complex, as you can see. So what you have to usually think about when you also envision the synthesis of such a molecule is how to make the carbon-carbon bond connections that form the framework, the underlying carbon framework of this molecule that are highlighted you here in black. And then afterwards, you have to think about how to install all the functional groups that give the molecular properties to this molecule that are highlighted in blue here. Now, these can be alcohols, amides, esters, ketones, and so on and so forth. And these give the molecule the ability, for example, to bind to a receptor, to a protein, and that gives us a lot of function. And with these things that you have to think about come a lot of problems. And about two problems I want to talk to you about today. The first one arises from the polarization that organic molecules have. So these are two ketones. In fact, it's the two times the same molecule. One is just flipped around. And the oxygen that you see here induces a polarization of these carbons here. So you have a carbon with a partial positive charge, and you have a carbon with a partial negative charge. And what is very easy now is to connect two carbons that have opposing charges, for example, this one and this one. And you form then a new carbon-carbon bond here quite easily. It's like if you have two poles of a magnet, the plus and the minus pole, they really snap together. So it's very easy to make molecules with a functionalization distance of 1, 3, as you see here, or 1, 5, and so on and so forth. What is very difficult, on the other hand, is to bring two carbons together that have the similar polarization, like these two, or the two red ones, to make 1, 2 or 1, 4 difunctionalized molecules. And this is something that we want to approach in our chemistry. Where is this important? Well, let's go back to the molecule that I've shown you before, the Taxol. They can identify really easily these 1, 2 difunctionalizations here, here, or here. And I brought you another molecule, which is erythromycin. It's an antibiotic that is generated by some bacteria. You can isolate also this. And here you also have these 1, 2 functionalization distances that are very difficult to introduce into a molecule by carbon-carbon bond formations. Just for completion, if you search again, you also find 1, 4 difunctionalizations here and here. There's a second problem I will talk about in the second half of the talk. That is the question how to also remove functional groups selectively from a molecule after you've introduced them, for example, and also to how to deconstruct organic frameworks back into smaller parts of a molecule. This is important because we usually, as organic chemists, we usually think only about the synthesis of complex molecules from smaller molecules, but very rarely about how to disconnect these molecules back into starting materials for another synthesis. So the bond disconnection and the defunctionalization may actually be quite important. So what are we working with? We are working with titanium and zirconium catalysis. Again, a catalyst is a small additive that you add into your reaction that accelerates the reaction, but itself does not get consumed in the process, which means that you only need small quantities of this catalyst to accelerate your reaction. This is then, of course, also an opportunity for an efficient and sustainable reaction. So now coming back to the metals, titanium and zirconium, this is the periodic table that you see here. This is the transition metal area. And you see titanium and zirconium here on the left side. So meaning that these are early transition metals, and they have a quite unique reactivity. It's complementary to the chemistry that we've seen this morning, for example, with copper or palladium catalysis. And these metals also have some other important properties. For example, they are base metals. They are very abundant in the Earth's crust, and they are non-toxic, which also is very good if you want to do sustainable catalysis. Now, coming to the catalysts that we employ, there are these metallocenes, they are called, these structures where you have a metal sitting here at the center. It can be the titanium or the zirconium, for example. Then you have two chlorides as ligands bound to the metal. And then you have these funny looking disc-shaped ligands, these cyclopentadienyl ligands that really have then the metal sitting in the center. It's like a sandwich complex. Okay, so coming to the first problem, I wanted to talk to you about how to make these 1, 2, 1, 4, 1, 6 difunctionalized molecules by forming these bonds here that are highlighted in red by connecting these carbons together. And to be able to do this, we apply a trick. And the trick is to give each of the molecules that we want to react with each other, or dysfunctional groups that we want to react, an electron. So we give now here to this molecule an electron, here to this molecule an electron, which means that we have an unpaired electron then afterwards sitting there on the molecule at this carbon here. And I mark this here with a blue dot. Of course, the molecule then has also a negative charge. And these unpaired electrons sitting at a carbon, once you have this, you call this molecule a radical. And these radicals really like to react with each other to form a new bond quite rapidly. And now it's suddenly very easy to make these 1, 2 difunctionalized moieties. Now let's replace these X atoms that are just placeholders with an oxygen, for example. Then you suddenly have 2 equivalents of acetone that you can then react in the presence of magnesium. Magnesium is a very strong electron donor. So you put magnesium metal in your reaction. It gives the electrons to these carbons here. Then you have these radicals. And the magnesium even helps to bring these 2 molecules in proximity to each other so that you can then very quickly form this bond and then you've made a molecule that's called pinnacle. So that's why we call this reaction a pinnacle coupling reaction. Now, we are not interested in doing reaction with stoichiometric amounts of magnesium, but instead we want to use a single electron transfer catalyst, a catalyst that is able to do the same thing just over and over again under much milder conditions. And the idea is that after the electron transfer, the catalyst remains coordinated by the substrate, which allows us then afterwards to control the reaction, meaning the fate of the reaction, for example, the coupling process in terms of also selectivity, regioselectivity, also chemoselectivity, regioselectivity, and stereoselectivity, all controlled by this catalyst. Now let's come back to the metallocenes, these titanocenes that I've introduced to you earlier. These really readily pick up an electron from zinc. And zinc is a much milder reducing agent than the magnesium. So then afterwards, you have suddenly an unpaired electron sitting at the titanium center. In the whole process, it also loses a chloride atom, which frees a coordination site, which allows then afterwards the substrate to coordinate to the titanium. So now we have a species that is a good single electron transfer agent and is able to coordinate the substrate to get to this mode of activation. It has been shown in the past that it can use this to make these radicals out of ketones, for example, and these radicals out of epoxides, for example, and then to do chemistry with it afterwards. Now, coming back to the pinnacle coupling reaction, exactly this chemistry has been applied to bring two molecules of an aldehyde, for example, together to form here a carbon-carbon bond. And this is the catalyst I've shown you before, and you only use 3 mol% in the reaction, which is 0.03 equivalents. The product is formed in good yield, but importantly also in good stereoselectivity, which means that the two OH groups that you can see here, they are pointing on the same side of the molecule, not on opposite sides. It's very important to be able to control the selectivity in organic synthesis. So this is a catalyst controlled thing. Now we were interested not in coupling 2 times the same molecule, but in the coupling of different molecules with each other. For example, a ketone and a nitrile that you see here to form this carbon-carbon bond. Then the ketone forms the tertiary alcohol here afterwards. The nitrile is getting converted into the ketone that you see here in the process. How this works, I will show you in a second. Now these motifs here, they're very important because they occur in a number of natural products. There are more than 1,500 known, more than 601 that you can find are biologically active. And in many cases, you have these cyclic forms here. So we wanted to start first making these cycles, which means that you have to bring the ketone and the nitrile in the same molecule here with a small carbon tether. So we wanted to connect these 2 carbons to make this product then in a titanium catalyzed coupling reaction. How does this work in detail? Well, the titanium catalyst gets an electron from the zinc. Then it looks like this. I abbreviated it here a little bit, not to confuse you, just to have an unpaired electron here, the titanium. It then reacts with a ketone. You generate a radical at this carbon here, and then the titanium sits afterwards at the oxygen here. Now this radical is able to add to the nitrile. This is another reaction that it can do. It forms this carbon-carbon bond, and here is stereocenter, which means again that the phenyl is pointing upwards and the titanium with the oxygen is pointing downwards. And it's very important to control this type of selectivity. You have a new radical here, which is getting then reduced and protonated. Then you have this intermediate, and afterwards you have an additive in the reaction that we put also into our flask that releases then again the catalyst, which now has chloride taken with it. This is then the first product that you get, and afterwards when you quench the reaction, so when you're done, you add the water and a little bit of acid into the reaction. This gets converted into the product that we want to have. So all that we need to do now is to convert this titanium species back to the one that has this unpaired electron. So how does this happen? Well, it's getting released, and afterwards it reacts again with the zinc. The zinc takes the chloride with itself and gives the electron to the titanium, and then it can do all this reaction process over and over again. Now, we found a catalyst that's able to do this reaction very efficiently, not only in a moderate to good yield, but also with a good selectivity. And then afterwards, we optimized the reaction further and we applied it to a bunch of substrates. We've seen this morning already a little bit, that as a organic chemist who is working in method development, you always need to show that your reaction is quite robust, that it tolerates numerous other functional groups, and actually that it's also applicable to a broad substrate scope, so that other people also want to apply your reaction afterwards. I will not go into too much detail here. I just want to show you that based on this concept, we have developed a number of other cyclization reactions that you can see here to make these products, and also intermolecular couplings where you bring really two different molecules together to form a new bond, as you can see here in these cases. This, for example, is now a 1,4 difunctionalized molecule, and this is a 1,6 difunctionalized molecule, to come back to the other functionalizations that I've shown you in the beginning. We've used these then afterwards also to study the mechanism of these reactions in detail. I will not talk too much about this now. We've used this reaction, for example, also to make a small natural product that's not as complex as the taxol that I've shown you in the beginning, but it's also one that you can isolate from these beautiful coral trees, for example. And this chemistry here we have applied to the synthesis of bioactive heterocycles and bicycles and so on. Now I want to talk to you also about the second problem. That is the question, how do you selectively remove a functional group, and how do you undergo deconstructions of molecular frameworks that you have built up before? And this is something of, let's say, well, maybe even global importance, because we organic chemists, and we chemists in general, we are very good at turning base chemicals into fine chemicals that can be also pharmaceuticals, polymers like these plastic bags, tires, and so on and so forth, through very well established coupling, polymerization, and functionalization reactions. However, at the end of the life cycle of these products, they usually end up in the dump, in the worst case on the environment, which is something you do not want to achieve. What else you can do is to just burn them, having a total combustion that at least gives you still some energy out of it, but it also comes at the cost of CO2. Then the other thing is, what you can do is you can treat them under pyrolysis conditions, so at a more controlled temperature, that then converts them into a little bit, or converts them a little bit at least back into base chemicals, but overall you always have a loss of value of your material. So what you want to do is to have a controlled deconstruction of these materials back into base chemicals, so that you only cleave the bonds that you need to cleave to go back there, so that you have a true chemical recycling that is then adding value and allows you to use these chemicals again in the manufacturing process. Now, we are nowhere there yet to achieving this, but I want to start doing some baby steps and learn how do we do the necessary deconstructions, and to develop some tools on selective carbon-carbon, carbon-heteroatom, and heteroatom-heteroatom cleavage reactions. I want to start with telling you today only one simple process, which is the removal of one single functional group from a molecule to put an H there, so a hydrogen there instead. So we've started looking into this with titanium chemistry again, where again, the titanium catalyst with an unpaired electron then leads to a cleavage of this bond. It's just chopped in half in the center, and then you can use this to get there. I will not talk about this now. I will speak about a second process, which is a zirconium catalyzed reaction, where we envisaged a process where we end up in a scenario like this, where you have the carbon with the X bond here, yeah, and the zirconium sitting at the carbon next to it. And now the zirconium is able to take this bond and deliver this bond over here. So it's just taking and removing this X. And then you are also able to get to this difunctionalized molecule in a catalyst-controlled way. How does this work? Well, first of all, we want to apply this to molecules that only have an isolated heteroatom function. What are these heteroatom functions? Well, this can be ethers, amines, thioethers, very common functional groups. and then you have nothing else around. So these these functional groups, they are very inert usually. They just sit there in your molecule. It's very difficult to remove them. Now the problem is that you only have an alkyl chain here. So the catalyst, the zirconium catalyst, does not have much to grab on to this chain to be able to get close to this group, to able to remove it in this scenario that I've shown you here. So what we thought of is that we take molecules that have an additional group in here, an anchor group where the catalyst that can connect to, and then maybe move over here to this heteroatom. This is an alkene. It's one of the most abundant functional groups that you find in organic chemistry. It can also sit here, for example, here or here. And the idea was then that we take a zirconium hydride catalyst. So a zirconium is having then a hydrogen next to it, and it's then adding to this double bond. The hydrogen ends up here at this carbon, the zirconium ends up at this carbon here, but now it's far away from this hetero function that we want to remove. So the question was, can the zirconium move along this chain until it's here at this position so that can efficiently remove this hetero function? And this is something that the zirconium already knows how to do very well. You end up with this intermediate, which afterwards gets reduced further to a final product. So overall, we envisaged a complete defunctionalization of this molecule to an alkyl group. The first thing I want to tell you, yes, we were able to develop this method. We've demonstrated it on 16 examples with a catalyst that looks like this. It's a little bit different from the one that I've shown you in the beginning. And importantly, we also have lithium aluminum hydride in there. That's a reagent that is able to convert the zirconium catalyst into a zirconium catalyst that now has one chloride displaced with a hydride, so with a hydrogen atom. So the lithium aluminum hydride just does this. It displaces one of the ligands with a hydrogen. And I abbreviated again the catalyst a little bit here so the mechanistic picture is a bit easier to understand. So what this catalyst does then is it approaches the alkene and then connects to the alkene by an addition reaction. So I have the hydrogen now sitting here and the zirconium sitting here. And importantly, this reaction is reversible, so it can go back also. So once it has added, this molecule can here also flip around. So these chains here, they're very floppy, so the molecule can twist around, and then suddenly you have another hydrogen here. So the catalyst can now decide if it reacts backwards or if it reacts forwards and removes now this hydrogen. And now we've suddenly moved the double bond that was here before, one carbon-carbon bond further. And you see where this is going. So the catalyst now flips around, adds again, and then it's sitting suddenly here. And it can does this whole process over and over again to remove now the next hydrogen, flip around, add again, and then after a number of hop-ons, hop-offs to this molecule, it suddenly sits here next to the functional group that we want to remove. So it's a dynamic process, and the catalyst is able to do this back and forth until we can then finally undergo this beta-oxygen elimination reaction. This is a reversal process, so the catalyst disconnects then afterwards, and all what we've done now is to move this bond over here and to cleave off this functional group. Now this reagent comes in again, it removes this group and replaces it again with a hydrogen, and then this can react again with our molecule, so it sits then at the end of the zirconium, and this is, well, it's a position where the zirconium likes to sit, it's quite stable, until the aluminum hydride comes again, now cleaves this group, we regenerate the catalyst, it does more transformations of our substrate into the product and so on. And this is then the intermediate that we have in the reaction until we kill the reaction again by the addition of water. Now we do this, the aluminum is getting chopped off, and then we have our final defunctionalized product. So overall, thinking on organic synthesis sense, this is not a very good reaction that you want to have, because you remove two functional groups, and usually, I've told you in the beginning, we're more interested into installing functional groups. But if you think about new concepts about removing functional groups, especially selectively, then this may be another step forward and a thing that can be applied in the future. Anyway, what I still want to show you is that we can also use this intermediate in an organic synthesis sense. So we can replace here the aluminum also with other functionalities by reacting this intermediate with other reagents. So you can put a boron here at the terminus, an iodide, a bromide, or a deuterium. So you can actually convert this functional group also very efficiently into other functionalized molecules. However, this is a different story. I want to close now and show you, give you the last slide, an overview about what we're all doing. So I've told you about these coupling reactions, these defunctionalization reactions, especially the remote bond activation I've shown you in the last slides. Then we are also working on the design of these catalysts that I've shown you, and about the mechanistic studies, and also on how we apply our methods in organic synthesis of natural products and heterocycles. I want to thank my group. It has grown over the past years. This is a recent photo from, I think that's last summer. I want to thank all my co-workers, our funding agencies, and I want to thank you today for having me here and for being, allowing me to be part of this great symposium today. Thank you.
Thank you very much, Jan. It was a very interesting lecture, at least for an organic chemist, as I am.
Yeah, I hope everybody could follow.
Yeah, I think we don't have much time, but maybe have time for one question if anyone in the audience wishes to ask a quick question now. Otherwise, if not, then I suggest that we take a 10 minutes break and then we come back and to this panel discussion, and then everyone can ask questions to all the speakers. So thank you very much again, Jan, and then we continue 15:05.
Thank you.
All right, welcome back, everyone. It's 5 minutes past, so we'll start this discussion. The way we will do this, normally you would see people in a given order. Now, obviously, all of us have the people in different orders. So I'm going to use in case we need an ordering, we'll use the same order as you gave your talks. But let's see, we'll probably keep it fairly open. And importantly, we invite everyone who has listened during the day to ask your questions using the Q&A function on your screen there to the bottom right. While you think about questions, maybe we can start with asking you speakers about your impressions of the day, whatever they might have been based on the talks you've heard and your own talks and thoughts that came up. So maybe I can start with Neil to see what your...
Oh, I thought it was great. Really interesting day. I was enjoying Melanie's talk when the point at which she said, which didn't sound like a very interesting chemistry problem, but as we dug into it, we realized the interest there. And that was making me think about how I think real world applications, which I think we saw a lot of today, can convene a group of people around a challenge and open new doors. And I really liked the way that the theme of the talks was sort of centered around that it's all inspired, well, I need to do this thing. And when you start having to do this thing, it makes you think creatively. And so we like playing as scientists as well. We like to sometimes just go off on our own directions, follow our fancy, but it's you know, it's that combination of a bit of play and a bit of direction that I think shows science at its best. And I really enjoyed the aspects of that we saw, I think, almost across the talks.
Yeah, thanks a lot. Good. Melanie, if I move on to you.
Sure. Yeah, I also really enjoyed the day. I think I loved Neil's talk on machine learning and sort of the big picture view of that. I think many times we see the applications, but I just love to kind of hear about it, from the perspective of sort of science history and sort of big picture, and it was really fantastic. I also, I thought one of the things I wrote down was actually at the very end when Jan was talking about sort of breaking bonds and degrading bonds, because I think that's something that chemists are always thinking about building things, right? This is our thing. We want to make bonds, but really, especially as we make more and more stuff, polymers, and even some of the bonds that I was talking about making today, part of the reason people want to make them is because they're not degraded easily. But as you think about the kind of pollution that's going into the environment, and how that's going to have repercussions on the environment, I think that breaking bonds is really important. So that really resonated with me as well.
Thanks, Melanie. Thanks. Arno, your feelings, comments?
Yeah, like overall, I think my sort of like the main thought I have after today is that why am I not attending this kind of things like more often? Because as a junior faculty member, I typically like rarely exit my own like research bubble in a sense. And like today, there were like things that I'm very familiar with, and people presenting who I'm worked with, but then like also like things that I'm not familiar at all with. And for example, like these talks on chemistry, I really enjoyed them, partly because my both parents are chemists. But then like I'm just like wondering that why am I not like participating in these sort of like things where actually more broad than just sort of like staring at your like inside your own research bubble kind of. So that was sort of like my thought after like listening to all the talks, that I really liked sort of like the level of the talks, such that even though I'm like don't know much about the other things, I could still follow, and that's really good.
Yeah, that's a good point. Makes me think of an advice I got as a young PhD student. You should always read the book next to the one that you intended to read. Typically don't have time to do that, but it sort of makes a lot of sense. Every now and then you should. So good. Xiaodong, what your feelings, comments?
So I would like to share the same view as the previous speakers. Really, I think this is a very good platform for like multidisciplinary field research. So that actually I learned a lot from the background of history of machine learning and what was the base and what you can do, and also this fascinating synthesis approach that Melanie has been doing, very great to be able to design like a molecule all the way to make the functions, and also the Dian that for the chemical synthesis, and it's very important to think about the sustainability, also to be able to see not only to make a product, also to how to recycle the product and to make use of this instead of like put everything into the waste as a waste product. And also like a lot of machine learning part, I really think that there will be a lot of important applications in the field of chemistry, and so it's like inspiring talks. I have learned a lot from this symposium and the lectures. Thank you.
Yeah, thank you. And then we move over to Nicholas.
Yes, I also really enjoyed today and see this broad spectra of various applications, which I'm not familiar with, and also the areas in machine learning, which I'm more familiar with, but it's also interesting to hear different thoughts. So, I mean, since I'm also interested in like the interdisciplinary work between, in this case, physics and machine learning, I mean, I always want to, when I hear these talks, to think how can machine learning be applied in these settings? So if I will be happy to discuss these issues further.
And then we move over to Jan. Thanks, Niklas.
I just had to turn on my audio, sorry. Yeah, I think I agree with everybody that it's really cool to have people from other disciplines to hear the talks, to look a little bit beyond your own horizon and to learn about new things. I think it was amazing what is possible today, just to, that you have the possibility of depth perception with one camera, or that you can measure the magnetic fields and use this really for new technologies. Also, how important ignorance is in the terms of research, for example. And yeah, I found this really amazing to have this all in one big symposium.
Yeah, cool. Thank you. Thank you all. We have a question that came in from Jakob here. So maybe I read it up loud and then let you think and answer as you wish. It's mainly directed to machine learning AI. So the question is, what do you think about the role of formal verification in machine learning / AI? Will the difficulty of verifying machine learning models hinder their applications going forward? So I leave the word open.
I can probably have a start on that. I think it's a fascinating question, and it actually goes to the core of, I mean, I often think, well, automatic control techniques are very similar to ML techniques, but they're ones that can typically be well verified or have things proven about them. And so sort of improved mechanisms for verification are very important for complementing sort of certification methods. Like typically we've done everything empirically, and you know, that's not good enough for the sort of things that we'd like to do. But I think there's a challenge as well, because people put too much store by verification. The whole thing about the sort of the Hydra thing and deploying things in the real world, when you deploy something in the real world, actually proving behavior about it can be a weakness. So my favorite example would be is if I can guarantee that a driverless car is never going to crash into another car, I can simply steal that car by putting 4 cars around it and driving off with it, right? Because I know something. So there's something very interesting about humans in the real world is you know, the reason you don't walk out in front of a real driver is you know that there's a probability they'll kill you. If you knew that the driverless car will always stop, you will walk out in front of it every time, and that will cause chaos. So there's 2 sides to the whole verification thing and proving stuff about a system like that. But I think it's an incredibly important point and a really interesting area for research.
Mm-hmm.
Maybe I can continue. So I think I feel that the question sort of like leans a bit towards like good old-fashioned AI to like AI methods with like formal reasoning and so on. And then like the kind of the opposite end is maybe what we machine learners here represent, sort of like the more like machine learning community, which has been criticized for like this like cowboy attitude that we just come with our models and shoot around with the models, and then we ride off without actually sort of making sure things actually work. And I think that is actually a bit of a problem, or at least has been before these things actually started to be applied. And you still stumble upon these kind of embarrassing things that things haven't actually worked out in the way they should have. So I think this is kind of the question is a very good one, and something that probably will be quite topical in the future as well. I don't have any solutions to provide yet, at least.
Mm-hmm. Mm-hmm. Let's see. Good comments. Let's move on. So there are several questions coming in here. One which is very much related to the title, focusing on the uncertainty part. So the question is wondering how you think of how do you conceptualize uncertainty. So 3 different parts here. Can uncertainty be quantifiable in general? Are there different types of uncertainty that you can actually compare? Can such an uncertainty quantification be incorrect in some sense? And And if so, how do we assess that? So this is a set of really interesting and quite complex questions, I would say. So what are your thoughts on this?
Try 30 seconds on it. So obviously I was advocating entropy as a measure of ignorance, and I think that's the standard measure. And yes, if you do translate things to entropy, you can combine them in some way. But I think that there are challenges to that. And here's something that I'm fascinated about. If we decide that all our uncertainty quantification is based on probability and entropy, that means we need models of what is going to happen. So we need to have a description of what is going to happen. But I was very taken by something my old mega boss at Amazon said, Jeff Bezos, when he's thinking about the future. He said, I can't tell you what's going to happen, but I can tell you what's not going to happen. And what's not going to happen is people won't want to pay more for stuff. They won't want it to be slower to be delivered, and they won't want less diversity of choice. And I was very taken by this because it's the opposite of what we do in probabilistic modeling. So in probabilistic modeling, we're trying to define everything we think is going to happen. And then here, what you're doing is defining what's not going to happen. And that's much, much more robust. And I think really shows some weaknesses in a lot of the way we're doing things when we think about that type of prediction. And it's very easy, I think, for humans to assimilate that. Yes, maybe we'll be flying cars, maybe we'll, dogs will sprout wings or whatever in the future, but people won't be saying, please, can I pay more for this thing that I was paying less for yesterday? We can accept that. And I find that fascinating. And I think there are domains of uncertainty quantification that try and take that perspective. Very, very under-researched. So part of my answer is, yes, use entropy. And part of my answer is, my goodness, we seem to be missing some stuff with our dependence on probability.
Mm-hmm.
Yeah, let me jump in. I was thinking about in a bit other direction as a chemist. I was thinking if we look back in history, the past, let's say 2 centuries, there have been enormous changes thanks to science. So for example, the way we can communicate now, the way we can quickly travel, the way we can access food, it's all the result of scientific revolutions. On the other hand, we can also see it so that what we have done has resulted in all the pollution, global warming, overpopulation. So we have solved questions, but we have caused other ones. And I wonder what you think about whether we can solve the challenges that we have today without causing future problems, or is it inevitable that when we solve the questions today, we will cause new problems? And maybe I just give the word first to Melanie.
Yeah, I mean, I think it's an interesting question. I think it's always the case, that there's sort of unforeseen consequences of anything that you do, and I mean, I don't know, my son is 13, and they've been doing some biology in school, right? So they're modeling what happens when you have, they have all these models, where you can model like, okay, how many foxes and how many rabbits do you have per acre of land, and then you put a couple of foxes and a certain number of rabbits, and they show, you see the sort of changes in the population and how the foxes will eat the rabbits, but then the grass grows, and then I think it just, that's what it sort of makes me think about when we're doing chemistry, right? And you say, oh well, this element is really abundant, so we're going to use it, but then it turns out that there's some issue with sustainability of getting it out of the ground, and then you solve that problem, and then there's some other, so it's always a jigsaw puzzle, I feel like, and I think I think that plays into the uncertainty that you have to do the best you can with the sort of assumptions and knowledge that you have at the time in terms of pursuing, for example, sustainable chemical synthesis or chemistry or whatever, but that ultimately it's going to introduce new complexities.
Anyone else? You have some thoughts about this?
maybe I can say something. I completely agree. I think to predict the consequences, it's difficult, but based on our knowledge, I think we get more and more aware of the impact. What we are developing today will be the impact for the future. And I think as a scientist, I think we know better, and we should really take our responsibility to really to think when we design a molecular reaction or a method, that what would be the impact for our next generation, for the society, for our Earth. And I mean, I was thinking about the Nobel Prize last year on the CRISPR technology. This is, I mean, there are lots of impact, and this and for human beings, and there are also risks, and we need to really to understand that and to be able to take the responsibility. And I don't know if the artificial intelligence and the machine learning can help us to predict the consequences, and yeah, so to be aware that what as a scientist is going to do and are doing.
I think that's kind of one of the dangers. I guess that was one theme of my talk. I don't think that we can solve that with machine learning and AI. And I think it's another example of this scientism that it's like science is great, but the problem we have with it, as we all know, and as I think Arno was alluding to at the beginning, is we're very much in our silos, focusing on solving very, very difficult problems that require a lot of effort. And that sometimes limits our contextual horizons and prevents us from seeing all the possible outcomes and all the possible other ways of solving things. I think we've seen that particularly in the pandemic. I mean, I think actually, you know, we point the fingers at scientists, so politicians, but I think some scientists' behavior has just been embarrassing in terms of going in the media and making extremely strong claims about things where there's a lot of uncertainty involved. And it's a consequence of this sort of scientism where they've got this narrow field of expertise and they're right in their individual domain, but they don't understand that there's a broader context, that there's things that aren't a function of their particular domain that needs to be considered. And that's why I really sort of like this point about what's going on at Uppsala with AI for research. And also, if you look back to the original formation of the academies, there was such diversity of conversation across these things and respect for other people's opinions. And we need those conversations going. So I feel, Xiaodong, that almost we could get there, but I think the way we would get there is by accepting the commonalities to our fields and rediscovering those. And I think machine learning is one way of doing that, because the reason it's widely deployed is because data comes up a lot and the mechanistic assumptions we're making are relatively weak. So I really hope it has this sort of convening power to get more of those conversations going, where we're getting a broader contextual understanding of the type of societal problems we're trying to solve.
Yeah, I mean, I agree. Machine learning and AI will probably help us to extrapolate from certain data points a model that will allow us then to predict or to improve something afterwards. But I think what it cannot do is to bring in points that cannot be foreseen. So the factor of serendipity that also is very important in research, or what we chemists call maybe a chemical intuition, why we should set up a reaction. Or what we humans are also able to do is to use the force of imagination, to think beyond the borders that are there, that is beyond the training set, to also incorporate things that are unforeseen. Coming back to the pandemic, for example, everybody knew that mutations would happen, but also nobody really included it in the model in predicting how long for example, our lockdown would continue and how the whole pandemic would evolve. So I think this is very important.
Yes, so I also don't think that machine learning and probabilistic models are like the ultimate solution to quantify all uncertainties that there are. Since, I mean, as soon as you employ a model, which you do when you employ a probabilistic models, you do make some assumptions. And if these assumptions doesn't cover all things that could happen, I mean, even though you have a probabilistic model, you won't cover that uncertainty. So that, I think that was very important with this disciplinary work that you always discuss with those who know about different fields to sort of enhance our probabilistic models to also include those effects which we couldn't foresee by just looking at the data.
Yeah, maybe let's take a question from the chat as well. I read it, it's from Jakob Nyberg. Is the increasing usage of fluorinated carbon molecules a potential issue for the environment?
Yeah, I think that that's right. I mean, I think that as we've seen in the atmosphere, you know, with you know, sort of volatile fluorinated molecules, as we're seeing now increasingly in the drinking water, with some of the molecules that are used for manufacturing, you know, the molecules with fluorines in them are useful because, you know, Teflon pans, things don't stick to them. Fluorinated materials are really useful in refrigerants, for example, which is what all the CFCs are. And similarly, as I said today, they're useful in agrochemicals and pharmaceuticals, but as we make more and more of them, they are going into the environment. And I think that, you know, pharmaceuticals, it's a pretty small amount. Agrochemicals, if you're spraying that on a field, it's actually quite a lot. So I think considering how to break those down, I think there's interesting questions of could, you know, enzymes evolve to do that? You know, could bugs evolve to do that? That really hasn't been observed, you know, to date. But I think that there's interesting questions there for sure. So, I mean, that sort of speaks to the sort of life cycle of any molecule that you make or any product that you make, and how, you know, thinking about where it goes and what's going to happen to it.
Yeah, I agree. I mean, these fluorinated molecules, you said it in the beginning, they have no biodegradation, so they just stay in the environment. And that has become a big problem, for example, with these fire extinguishing foams they used on airports, for example. So these are foams that have carbon chains that are polyfluorinated. And these molecules, they just accumulate in the environment. So you find them in the tissue of animals, you find them everywhere around, even if it's only in ppm amounts. And this is because they just don't degrade over time. So actually activating carbon-fluorine bonds or to degrade these molecules is quite a challenge if you don't want to burn them, and some of them don't even like to get burned so well.
Yeah, I fully agree. I was thinking actually about the selective carbon-fluorine bond cleaving reactions while listening to your talk, Jan, after Melanie's. It's maybe a nice field of research.
Yeah, I mean, that has been also a big topic in organic chemistry. I mean, to use carbon-fluorine bonds to do cross-coupling reaction with this. So there are other groups that are working on this quite intensively.
Yeah, Thomas, do you want to jump in with some AI questions from the chat maybe?
Yeah, I think our Hemin has a question. So let's see, and then we will come back to the chat questions or the Q&A questions, sorry. So Hemin, I think you will be able to jump into picture here.
Right, thank you very much, Thomas. Well, when I look at Neil's screen, I see he has a nice Mac Plus behind on his shelf. So it took 20 years for Apple to go from that box to iPhone. And if you try to put that in perspective in relationship to the human evolution, so why are we not going as fast or how far can we get with both artificial intelligence and maybe the chemical reactions happening in our body that prevents that kind of evolution?
That's really interesting. And actually, I keep thinking a lot about, like, so our intelligence has evolved over, well, if you see it as part of life, over billions of years. And like there are multiple intelligences inside us. I mean, our immune system is, you know, I don't know, it feels like it's as complex as our brain, you know, and there's this weird interaction between our immune system and our brain, and all life forms have some kind of form of immune system. And you see the computer and you see what it's done. But so my first thought on it is, the computer, as I said, has this enormous bandwidth and ability to communicate, but that one doesn't. That one had to have people sitting there typing into it. It wasn't even connected to the internet. So it had this super weird evolution in that the first computers had to have punch cards and had super low bandwidth communications, had no interaction with their environment. And then they've suddenly gone and they've created their own world. And now they are evolving in a sort of evolutionary way through machine learning algorithms being A/B tested on human subjects. And what I think is happening, here's the weirdest interaction, and I call this system 0. It's in a nod to system 1 and system 2, like the sort of fast thinking and slow thinking. They are evolving now to create this sort of vast system that sucks us in, that has found like, so I always think it's like, you know, like high fructose corn syrup foods are quite addictive for humans, because I suppose the idea is that they're stimulating historical, we find fruit. I guess like if you find fruit in Sweden or the UK, then this is like amazing. And then you just eat as much of it as possible, and your body wants you to do that. So fructose apparently stimulates that and causes us to lay down fat. But when it's constantly on supply, it's problematic. And when you look at social media interactions, well, I think the machines have found the cognitive equivalent of high fructose corn syrup. So they're providing you with that personal validation about your life, which was incredibly important in small groups. Like if Arno and I are at a Gaussian process meeting together and I say, that was a really great talk, you know, and he feels good. But now it's happening at this massive scale, and we're being drawn in to provide the machine with data, which I find kind of extraordinary. So having said all that, out of the two of us, we're far more robust than the machines are. And that relates to everything that we've just said. So they're designed for a specific purpose, and they can't handle these, you know, strange situations. I mean, it's amazing when you think our brain is capable of having evolved in wherever it evolved, in forests, in the plains or whatever, and now is doing all these things and looking at iPhones. And I think that actually that is still our ability to adapt cognitively and socially to these entities is probably the limiting factor on the speed at which technology can move. So everyone says everything's moving very fast, but I think fundamentally that time constant for us as people, us as a culture, to assimilate and work with these things is probably the limiting factor on how much they change us. Sorry, a bit of a garbled answer. I'll stop there.
Anyone else want to comment? If not, let's take another question here from the Q&A. This one is from Nils Einar, who asks the following. So almost 10 years ago, I'll try again. Almost 10 years ago, a group in California simulated a large part of the function of a mammal brain. The speed of the simulations was not too far from real time. What about AI and nerve system simulations today? Anyone who knows about the status there?
I don't know that work, but I do think it's so now I have to go to the other side because I've got a brain here. So I'm not a neuroscientist at all, and apologies if there's a neuroscience person in the audience, but the thing that strikes me about this brain is the bit that we're managing to recreate with deep neural networks is this sort of object recognition part at the back, the visual cortex. I sort of think that, to me, that's the bit that we share with lizards and birds and other animals. This is some retro function we fitted on more recently once we became mammals, and everyone goes on about it. But I'm becoming increasingly fascinated by this bit. And I don't know about the simulation in real time, but we can't do anything that this thing can do as far as I can tell. In terms of flexibility and robustness of movement, I mean, that's what a gibbon is using, combined with visual system a little bit, but the visual system is coming in here. The optic nerve is here. It goes into these parts first before it reaches the visual cortex. And the ability of this sort of brainstem to control our movement and to do these extraordinary things that are done across animals. I mean, we like to think it's all this because that's like about playing chess or something, or philosophizing. But really, you ask any control engineer about what that does, and you know, you can't persuade me that we're close to simulating what the immune system is doing in real time, the nervous system or the immune system is doing in real time. The complexity is just absolutely astronomical. I mean, so I don't know about that word, but I think it's incredibly difficult to even understand, like the devolution of sensing in these systems. There's some, you know, motor systems, some of this work is going on in your spine and it's being devolved down to your nerve systems because you can't afford to send all signals up to your brain and back because you might want a rapid reaction. I mean, I just, it's mind blowing. You know, don't tell me about solving Go. That's the funny thing, like the picture at the beginning of AlphaGo of two people around a Go board. Why are the two people? Why are the two people? It's supposed to be a person against a computer. Well, the computer can't move the pieces. And we don't have any machine that can move the pieces as elegantly as the human can.
Any other thoughts, comments?
I just want to continue on Neil's comment about the Go thing. So it's actually quite strange because like people were saying that the Go is such a hard game that it will take, I don't know, 20 years for computers to master Go and so on. And then in the end, it turns out that the harder part was grabbing the pieces. So that's just crazy.
Yeah, actually, and to know that, how hard that is, there's, I think it's called incipient touch. Ken Goldberg, who's a roboticist, told me about this. When you pick up a glass and it's filled with water, you can feel when friction is about to break. So you can feel as it's slipping. I mean, that is extraordinary ability. I mean, and that's the sort of ability that you're using. That I believe that there's a whole culture around how you pick up the pieces and clear the board in Go. I'm not an expert at all. But that type of ability to feel as friction is about to break, I think that's, so I asked Ken about it because I said, well, surely that has to be somehow devolved partially to the fingertip because the chance to send the signal all the way up into the brainstem and respond, it's just too slow. And he said, yeah, no, there must be something like that going on. And, you know, we can't simulate that. So at Amazon, people were interested in building machines for picking for obvious reasons. It's extraordinarily difficult to replace the human in that task.
Yeah, points to robustness again, I guess.
Yeah.
Let's see, let's pick another one here. An anonymous asker who says, is AI close to imagining truly novel things? And it gives a reference to OpenAI's DALL-E model. Fairly recent model. For those who haven't heard about it, you can just Google it, obviously, but it's basically a network that creates images from text captions. But again, what do you think about that? And the other things where people have used AI, or well, not people, obviously, machines producing music and so on and so forth. So what are your takes on that part of the technology?
So, I mean, so I'll go again quickly. I feel like I'm doing too many, but I'm going to try and relate it to chemistry. So that network that is mentioned there is this amazing thing. They've trained on like the whole internet in terms of text to get an understanding of what humans think. And then they've managed to connect this with algorithms that generate images, a bit like what Arno showed in his work. But then they can ask it things like, design a chair shaped like an avocado or something. And it does create these amazing things. But that's a mind-boggling large amount of data. that they're using. I mean, it goes back to what I was saying about the nature of that intelligence. And I think what Melanie and Jan were talking about earlier in chemistry is like how you're imagining these different reactions that can occur with a much smaller amount of data and a much smaller amount of understanding. So I think it's, you know, what Dali is showing, which is incredibly impressive, is just how much you can do when data goes to this unimaginable scale. But I think that we're going to keep seeing impressive things in that domain. My feeling is, though, that there's always going to be these regions where the problem is complex or the data availability is small. And things like when you heard Melanie and Jan talking about chemistry, you know, imagining what the right thing to intervene with, they're doing it on far less data than these machines can. And I think, but it also does lead to sort of questions about what is a truly novel thing. I mean, I don't really have an idea because everything we're picking up is derivative. I mean, I always think, so Nobel Prizes were mentioned. I definitely won't be winning one. But the funniest thing I think about the Nobel Prize is, you know, when it comes to the Higgs boson, 4 groups have invented it at the same time. So I find that totally bizarre, because why are we awarding a prize for something that was apparently obvious to the whole community? We represent it by one person. It's not novel in that way. It's a community arriving at an understanding together. And that's why you get multiple groups achieving things at the same time. And I think that's why I find the magic of being human so exciting, because it's those type of discussions. Again, I've gone on too long, so I'll stop. But I introduced chemistry. I don't know, Melanie, what she thinks about the chemistry angle.
I have a question to that. So I think sort of Jan alluded to this as well. So I think one of the magical things about chemistry and sort of, you know, is that you may run a reaction and you will find something completely unexpected. You know, this is, you know, and of course, you know, part of being a successful chemist is to have the intuition to recognize that it's unexpected and to recognize that it's unexpected but interesting, right? And so you have to kind of bin things as unexpected but I don't care, unexpected but really interesting, you know, et cetera. And so I guess kind of the flip side of this question then is AI going to, or is there the potential that by training on things we already know and expect, that you limit the possibilities as opposed to increasing the possibilities for, you know, novel things to arise?
I think that's definitely happening. So that's what's going on with embedding biases by looking at old data and training on old data and making decisions as they were made before. But you can see we can flip this around, because now we can start looking at what things. So I think AlphaFold's really interesting in that respect, right? I'm sure it hasn't solved the whole of protein folding, but it's allowing you to get quickly to a number of things that we don't expect, and then maybe start filtering out what standard things expect, and maybe start doing searches for what you're saying, Melanie, using the model the other way around. So starting to say, well, wait a second, is the experiment we observe unlikely under our standard expectation, and then get excited about that. So it's sort of almost to do it, to sort of say, well, that model's embedding something about our intuition and our data at the moment. And in science, I think this is a really interesting direction to go in. But it doesn't capture this observation I have. So I think that particular case is really interesting, because in AlphaFold, I think it's a really nice example of building a computational tool by combining domain expertise with data, deploying it on an important problem, but then ending up with a new tool that will hopefully allow us to go deeper into the same questions you were just asking, do more of it in simulation perhaps.
Okay, but does it always have, I mean, I don't know much about AlphaFold specifically, but does it always have to be something that you could conceive? You know, so I mean, is there always some component of
well, no, so another one. So in Cambridge at the moment, we're looking at quantum chemistry as an area, and what I understand is going on there is because the Schrodinger's equation is so difficult to solve, you can't actually look at these bondings in simulation, but you can start building machine learning models that learn from your solutions of Schrodinger's equation and give you an approximate solution to Schrodinger's equation, right? So the nice thing about that is that's a bit like, remember the game of life thing, that we've got to this point that we've discovered this entity exists. Now we can start trying to compute on that entity rather than trying to recompute that entity exists each time. That's been assimilated in our knowledge. And then maybe we can build systems that allow us to better simulate the molecular bonding at the quantum level, and allow us to do more complex, larger systems. Things like that, I think, would be exciting.
Would one way of looking at what Melanie said be that like machine learning models might find it like easier to interpolate? So like you might have some like observations of what happens in different cases, and then interpolating in between these sort of known cases and coming up with maybe something more or less unexpected there. But then what might be lacking is then the case of like really exploring something from data or known things. Then really exploring something completely unknown outside the observed.
I agree, Arno, and I think that's why I was trying to emphasize this point, that it's about the interaction between the human and the computer then, because the problem then you get is if the computer understands something in a certain way and is giving you some answer, you as a human, normally, like if I'm speaking to Melanie and she's telling me about some chemical reaction, I'm going to believe her, right? I'm not going to sort of go, okay, I doubt what you're saying about chlorine because you're an expert on fluorine. You know, I'm just going to believe her and accept that she knows that because I know who she is and what her background is, and we're going to move forward on that. But if a computer tells me something about a fluorine bond, how do I assimilate that? How does Melanie assimilate that? How does she weigh that against the other contextual things she knows? And know, because she's the one that can extend beyond and have the context and maybe the conversation with Jan that's given her an instinct that there's something new going on here. So I think there's a real challenge in identifying, as you sort of say, Arno, when are you in this regime where the thing's interpolating? What is the information it's interpolating on? What is it not taking into account? And what can you do to add to it? And that's an evolved, when we have our conversations, we've evolved to do that together over hundreds of thousands of years. But when we interact with a machine, I think that's incredibly hard. And a lot of the interesting work is going to be done at that interface.
Yeah, actually, one problem that you have when you do these quantum chemical calculations is that you have to be extremely careful with the interpretation of the results, because the computer always gives you an answer, but you have to decide, is this now a correct answer, or is this something that is completely rubbish, and you have to maybe feed the computer different data. So yeah, I think this communication thing is a big issue in these regards. And another thing is that for years, for decades, we have tried in organic chemistry to find the correct path of synthesizing a molecule. So you always have several consecutive steps, and we have now huge databases of reactions that have been done in the past. And there have been attempts to feed this database now into a new program that then simulates the best way of getting to your target in the shortest number of steps. But it's only very few times that this has been successful. This was, of course, then a big publication somewhere, but it's nothing that can be applied on a routine basis. Actually, I'm quite happy about this, because otherwise I would not have the job that I'm having now. And people would not have to be in the lab trying to optimize a reaction, trying to realize a new reaction that has not been done before. This would be all predictable.
Mm-hmm. Yeah, I think the thing that's interesting about that is also that I think that, and I think that's why a symposium and a discussion like this is really useful, because I think that there's sort of a segment of people who want to believe that that machine learning and feeding these databases in to solve these problems in synthesis is going to solve every problem, right? And that's you know, that you know, and they'll write a paper that says we've solved every problem, you know, and then there's a subset of people that don't believe that there's any value to it at all, right? And so I think that, you know, being able to see the advances and then also see the limitations in the context of this and have a discussion about it is actually really valuable, because I think the truth is in between, right? I mean, you're still going to need people, right? And like Neil was saying, their interactions and their interactions with a computer. But on the other hand, I think that there's many things that could be done better and faster by taking advantage of these, you know, increasingly exciting and useful tools. So it's you know, but in chemistry, I think there's definitely many populations that are in one of those two bins, it's going to solve everything. It's terrible and you should never do it. And I think it's, it's an interesting that there's relatively fewer people in between.
I think that comes back to the importance of these interdisciplinary institutes and bringing people together around these problems to sort of get a calibrated understanding. I call that like techno-solutionism versus techno-skepticism. And everyone either is in one camp or the other. It's like, no, there's no possibility that this could be quite useful. It's either going to save the world or it's going to, it's absolutely useless. And we've got very few technologies that actually have ever done either one of those. So it's kind of fascinating. But it's a nice way of, I think the difficulty we have is, particularly if you're an expert in a domain, this stuff is being thrown at you, you're reading about it, you're getting the papers like Jan just said. Every time it works, that's like a Nature paper. And everyone has to run around looking after it, and trying to recreate it. And you never hear about the times that it doesn't work. So everyone feels the obligation to sort of understand this stuff. But if you're senior in your career and it hasn't been there, I mean, most of our human intuitions are based on the time we've experienced interacting with certain things, whether it's chemical interactions or whatever. And if this technology is coming in from left field, it's very, very hard for people to have a calibrated decision around it. And a lot of what we're doing in my team at the moment is actually working with leaders, whether that's governments, whether that's like chief execs in companies, or whether that's scientists, just to help them develop a calibrated understanding of, no, it's somewhere in between. It won't save the universe. It won't be useless. It's somewhere in between.
I mean, there are several aspects in daily life where machine learning and AI has already been applied. And I've noticed now that I've been in contact with many Swedish institutions and so on, because all the texts are in Swedish. So the Google Translator, for example, is a magnificent tool that got much better over time using this AI technology. So I think there are many ways and niche applications where this can be actually be a game changer in the future, especially when it comes to communication.
Yeah, and it's a really good example of where there's a lot of data and that quantity of data. So I was at Amazon when they started building their translation system from scratch, and I knew the guy that was doing it. And he said, look, it's just about the quantity of data. We now need to scrape the whole web, basically, and find every aligned transcript on the web in order to perform well at these things. So if your language is Swedish, you're sort of okay. But if your language is Ugandan, or a sort of low resource language, it's still kind of problematic. But yes, it's a really nice example of something that's come an enormous distance. But I think the problem is people don't get the difference, say, between that and then the sort of chemical reactions you're working on, right? So, and that's why I'm always trying to work on the need for data and the uncertainties to try and get people to see what will work and what is going to be a bit harder to do.
But Neil, this black and white kind of perception human beings have, do you think AI would be better in recognizing the gray shades in between?
Well, interesting. It's actually, there's I don't know, one of my ongoing frustrations is when I built classification models with Gaussian processes, they weren't as good at that as what I'd hoped that they were going to be. I guess yeah, I don't know. Sometimes I think my main point now is, I guess if we rely on them to do that, that's problematic. And actually there's a major question about how do they present their uncertainty. So if Melanie and Jan have a discussion about a reaction that they think is going to work, it's really interesting how do humans explain the bits that they're certain about and the bits that they're uncertain about. And they'll have a dialogue. And that dialogue will often, they won't sort of say, and it's 75% likely to happen in this way. And then everyone will go, I'm combining that with my 48%. And now we have the updated probability, which is like what the Bayesians would have you believe. But they may tell a narrative, oh, I think it's going to be like this because of that. And then Melanie might say, and then Jan might say, but I've got this other experience and I'm saying it's like because of that. And then Melanie might say, oh no, when I said that, I didn't mean in the way you're describing now, because there's I think they're trying to reach is some pinch point that they agree on. So they've got this varied understanding about the broad thing, and they're trying to negotiate down to the bits of the question that they agree about, so that then they can explore the bits that they don't agree about. And so even if they do express this type of thing with shades of gray, that's what I mean about the challenge is, how do we express it? How do we bring that into the conversation in a reasonable way, such that a couple of clinicians having a discussion about a patient can also assimilate this information into that conversation. So, I mean, like the likes of Arno, Nicholas, Thomas, and myself go on and on about, oh, it's so important to produce probabilities, but we never actually tell people what they do with the probabilities. Well, actually, maybe Thomas does a bit because he does control, but because that's really about the decision, and that's contextual depending on what the person's trying to do. And I think that's a major challenge.
I would like to talk about when you talk about for machine learning, you need the data. So big data will be very important in terms of chemistry, and especially like a scientist, we only publish the positive outcome of the data, and also very few data has been published. So this is like the difference between like a human who have a lot of intuition because you have trained, you have done a lot of experiments, and this has never been part of the data that's being like available for research. And if we were able to collect all the data, both the successful experiments and also mostly unsuccessful experiments, would that be a much better platform for applying the machine learning?
I don't know if Melanie and Jan would like to say something about that and how that is in chemistry, in terms of the challenges and negative results.
I mean, it's true that usually you only publish the stuff that had worked, and but I also think that there is a journal of failed results or experiments that have not worked or something like this, but nobody is basically using this. So yeah, it would certainly be a great deal of information, and it would certainly help everybody to know if somebody had already tried what you are trying at the moment, and but the information would be around that it doesn't work, so you don't try. Yeah, I mean, trying 2 times a failed experiment is not a good idea to start off with. Yeah.
But so, I mean, I guess I would say 2 things. I think on the one hand, I think one of the most important things of intuition that a human has about something is actually about things that don't succeed as opposed to about things that do. So I think that's, I mean, many of those, everything that we failed at, you see this in graduate students, right? They'll go and do something and you'll be like, why did you do that? I would never have done that because I just knew that it wouldn't work because how did I know it? I don't know. So I feel like a lot of the things that won't work in some level are things that you never even would publish because you just know, but I don't know how you know, right? So I think that's one thing. I think the other thing though is I actually love it in my lab when someone tries something that someone else has tried before, because usually they don't try it exactly the same way. They might be trying to make the same moth, or the same, do the same reaction or whatever, but they'll do it slightly differently. And actually we've had, a lot of times, I think one of the things that I found is sometimes you have to just kind of kill off a project for a while and then resurrect it when all of the people that used to work on it are gone. So they don't know that this is a bad project, right? And then they come back and they do it, and then suddenly they get it to work because they go back and try things without the inhibitions of thinking that they're not going to work. So, it's an interesting thing because I feel like in some ways telling people this experiment will fail might inhibit them from trying a slight variation of that experiment that actually might be successful. So I don't know. I don't know what you think, Xiaodong, but that's a, yeah, as an experiment.
Now you talk about the reproducibility, so that it's also important. I was just thinking that if there is a way to collect all the data, now you have the electronic lab notebook, and so be able to use this as a base of knowledge to be able to for the data mining or for the machine learning. that would be probably helpful to generate more robust pathways for reactions or design of molecules and so on.
I think, again, sorry, I keep hammering the interdisciplinary thing, but this is a conversation that's been had a lot in biology and computational biology. And that's because I think the data became sort of important, very important there sort of 25 years ago. And I think that most of the things I've learned is by seeing that community and how they operate. And again, I sort of feel that that's where machine learning can help, not by automating this, but by actually allowing chemists to get together with computational biologists and hear what their solutions have been, and what's worked for them and what hasn't worked for them. Because it's that sort of sharing of knowledge about how we do this, which I think is going to unlock, I mean, Melanie's point taken that it is actually quite good if you often repeat some stuff and an experiment. What does it mean that an experiment was done? I mean, even that's a little bit done by whom? But those type of resources, I think in computational biology have been incredibly successful. And I see in the chat that Platzer Bjorkman has mentioned open science, and yeah, I hope that somehow ML is a gateway drug to open science. I know normally gateway drugs lead to worse things, but in this case, it might lead to something very positive.
I'm gonna use this pause and just remind us that we are getting close to closing time here. So we still have several interesting questions, but again, in the interest of time, I'm gonna hand over to. First, I'd like to thank you all for this wonderful day. Thank you, and then I'll hand over to Hemming, who will say a few closing words.
Well, thank you very much, Thomas. I also copy what he said. I thank you very much for your excellent talks and stimulating discussions. When we were discussing this year's Celsius-Linnaeus Day last year, we were not sure whether we were going to have it online or on site. And with time, during Christmas, we realized that an on-site gathering would be impossible. So we decided to go online. And I was a little bit worried, although I didn't share my worry with my colleagues in the committee, that maybe the technique would not help, even when we would be talking about artificial intelligence, but maybe the technique doesn't get us there. But I'm of course very glad that things worked fine. And I'm thrilled that we had excellent talks and stimulating discussions. Normally, as I said, we have Celsius-Linnaeus Day on site, and I hope that we have it 2022 next year on site. And I hope that the foreign guests who couldn't come to Uppsala this year, I hope at some stage in the near future we can host you here in Uppsala and you foster a more collaboration with Uppsala researchers here. Having said that, I have also to thank one specific person who worked behind the scenes and made this day possible in many ways. The practical details were all taken care of by Mrs. Karin Tellenberg. Well, she has been written to many of you, but she has organized all the practical details. Well, if you don't know how she looks like, if you look at the list of participants, you see my name, but the picture is not mine. The picture is hers, actually. So that's how she looks like. With that, I thank you very much once again for making the day possible. Take care and be safe. Thank you very much.
Thank you.
Thank you.
Thanks very much for inviting
Bye-bye.
us and hosting us, Hemming. It was wonderful.
Yes, thank you.
And thanks to Karim in particular as well.